Yeah. All ready? Go.
The broadcast is now starting. All attendees are in listen-only mode.
Greetings. Welcome to the Fiatech webinar. Thank you for joining us today for the Advancing Asset Knowledge through the Use of Augmented Reality Technologies. Before we get started with the presentation, I'd first like to review how to use the GoToWebinar system to optimize your experience today. You've all been put on default mute settings due to lots of participants on the call. You're encouraged to please forward any questions that come up in the webinar using the Questions tab. The questions will be read anonymously at the end, so please send them as you see fit. Use the orange arrow to minimize control, or the control panel. You can also move around the webinar interface on your screen. Recording and posting of the webinar in Webinar Archives is available at fiatech.org. It might take a couple of days to post, but it will be there, as I say, in a couple of days. Thank you for attending, and I will now start the recording. I'm Stuart Young. I represent Fiatech in Europe and the Middle East. I have two roadmap elements, Roadmap 4 and Roadmap 8. On behalf of all of us at Fiatech, I'd like to thank you for joining us today for, once again, advancing asset knowledge through the use of augmented reality technologies. We've an hour set aside to learn from Manny Golpavar-Fard and Justin Howe about augmented reality. But before I introduce the speakers, I'd like to remind you that Fiatech is a member-based organization with an objective of accelerating the deployment of technology in the capital projects industry. We have nearly 100 member organizations and partners, including academia and subject matter expertise, and always welcome new members to participate in our activities. If you're interested in joining Fiatech or would like more information or have ideas on topics for future webinars and projects, please drop me a note at young@fiatech.org. I'd now like to welcome and introduce Manny Golpavar-Fard and Justin Howe. Before I get to Manny and Justin, I'd just like to amplify what I said about Fiatech. It's an international community of passionate stakeholders all working together in a collaborative fashion to develop innovative practices and technologies. Fiatech's members are united by one goal, and that is to make a step change improvement in the design, procurement, engineering, construction and maintenance of large capital projects and assets. Global activities, we have 30 international members across all those areas of the world. We also have an advisory council based in Europe, and we meet at regular times throughout the year. We deliver productivity and efficiency through our projects, our networking, our technology exchange, and our awards and recognitions program. Fiatech was created by owner companies within CII, and it includes members and partners that represent a broad range of industry stakeholders. The value that members get on collaboration on projects: we have an antitrust protection policy, we leverage resources, we have leveraged resources and funding, we leverage risk, we have a competitive edge, or we develop competitive edge, we have project deliverables, we always have on hand access to subject matter expertise, we network and we team build, but ultimately we get results. Getting involved is quite simple. Participate on projects, attend the annual conference and members meetings, attend webinars like today, propose a project, lead a project, serve on a roadmap team or on a committee, review projects from the website, host a workshop, but most of all engage. The augmented reality project is covered under element 7, new materials, methods and products. And if you care to take a look at the website, you can see not just element 7 and augmented reality, but you can see a whole host of other projects and lots of very interesting information. Element 7 is one of 9 elements within the Fiatech roadmap, from design through construction to life cycle data management. Introducing the project team, we've got Golpavar-Fard from the University of Illinois, and we've got Justin. But first of all, I'll introduce Manny. Manny is a assistant professor of civil engineering at the University of Illinois. Manny is the director of the real-time and automated monitoring and control lab, where research focuses on sensing and augmented reality visualization of construction performance metrics using digital images, site video streams, and building information models. He's co-founder and CTO of PowerWorks, an award-winning startup company that focuses on producing the next generation of markerless mobile augmented reality mobile apps, and has been recognized with awards both at CES 2013 and SXSW 2013. His work has been in receipt of the 2013 James R. Rose Medal from the American Society of Civil Engineers. In 2012, he had the Best Journal Paper Award from the ASCE, also for constructing engineering and management. The Best Conference Paper Awards from 2012, International Conference on Constructing Application of Virtual Reality, and 2010, the International Conference on Innovation in AEC. The Best Poster Awards from the ASCE Construction Research Congress in 2012 and 2009, and the CII Annual Conference in 2010. His work has also been recognized by Fiatech SETI Award System in 2010 in the category of Outstanding Student Researcher. He is currently the Vice Chair of the ASCE's Data Sensing and Analysis Committee. Also on the call today, we've got Justin Howe. Justin is a part-time research assistant for Fiatech, whilst he covers his MS in civil engineering at the University of Texas, Austin. Originally from Massachusetts, graduated with a BS in civil engineering from the University of Hartford in Connecticut. Following this, worked for 2 years as a field engineer in a wastewater collection and clean water distribution company based out of Hartford. I'll hand over to Manny to get us underway. Manny, please continue.
Sure. I'm going to make Justin the presenter. Justin, please.
Thank you, Manny. So, to start off, I'm sorry, Manny, handed over the screen to me.
Can you make me the presenter again, please?
Yeah. I just need the controls, not the screen. Okay, sorry about that glitch there. So the question is, what is augmented reality? Augmented reality is a movement that's been around since the early 80s and was introduced in the movies. And whatever environment the hero in the movie was, he always had the most up-to-date information at his disposal overlaid accurately on his heads-up display. In real terms, we define augmented reality as a live, direct, or indirect view of physical, real-world environment whose elements are augmented by virtual computer-generated imagery. Augmented reality has a number of applications across existing markets. Consequently, when this technology is refined and improved, it will provide users a competitive edge and create a market advantage when offering the service to customers. This project addresses the business opportunity for indoor tracking of people, assets, and augmented reality applications for security, health, and safety, and operational maintenance of sites in the capital project sector. Presently, a number of traditional processes in the industry are labor-intensive and require a significant amount of paper-based activities to manage and control on-site data. It's hoped that augmented reality will provide engineers with all the specific information they require when in the field and the ability to access and edit information on site. As a result, the success of this project will create new capabilities and further the development of current methods and practices within the capital projects industry. The scope of this project has been designed and phased to include the four following proof of concept steps. First step is to merge simple and complex data into a Google Street View style visual with a static camera device. The second is to merge that same type of data into a real-time view. The second step is merging simple and complex data into a real-time view with a static camera device. The third step was to merge simple and complex data into a recorded video stream with a mobile camera device. And the fourth step is merging simple and complex data into a real-time view with a mobile camera device. To date, within the phases 1 and 2 of the augmented reality project, the first 3 steps have been performed and proved to be a success. As well as we will discuss in detail shortly. Phases 1 and 2 involve the utilization of 2 fully documented proof of concept trials and test beds to analyze the feasibility of augmented reality within the construction industry. Step 4, which again was merging simple and complex data into a real-time view with a mobile camera device, was not performed during these first 2 phases due to real-time location issues, which we'll discuss later within the last segment of this presentation. Step 4 will be incorporated into the third phase of this project. When the project team started this project, we had a very broad discussion about all the areas within the construction industry that could be improved by augmented reality. With refinement of the existing platform and capabilities, it's anticipated that the augmented reality project will help to resolve the construction issues highlighted within this slide. The use of various existing tools such as GPS and 4D modeling will likely have to supplement augmented reality to address some of the mentioned issues on this slide. Similar to the previous slide, refinement of the existing platform and capabilities will also allow augmented reality to assist with the operations and maintenance issues highlighted within this slide. The effectiveness of the capabilities mentioned within the 2 previous slides will heavily rely on the accuracy of real-time location services in addition to the accuracy of the overlay of 3D model data onto the live view of the site area being studied. Here, we're going to begin discussing what has been achieved thus far by the Augmented Reality Fiatech project. The M1 Junction 12 Highways project in the UK served as the first testbed. The construction project scope of work consisted of remodeling the surrounding highway and erecting a new bridge in the M1 Junction 12 area. The Augmented Reality project team chose this area, or the site, as a test subject for Phase 1 due to the fact that the construction was already installing fixed live stream cameras on site for security and construction overview purposes. The project team recognized a unique opportunity to utilize these newly installed cameras to prove that accurate overlay and building information modeling onto a live streaming camera feed is feasible. The objective of Phase 1 was to prove the concept feasibility of augmented reality, of augmented panoramas for the use of on-site monitoring on actual building sites. The first testbed included using the on-site static camera device to merge simple and complex data onto a 360-degree panoramic photo and real-time view of the project site. To give you a better idea, the 360-degree panoramic photo was very similar to what you would see in a Google Street View style visual. And the real-time view of the project site was produced with a live camera feed. First, a 3D model of the structure currently being built was provided to the project team. Following, the team attempted to overlay the model onto a panoramic photo. However, the team could not determine how to accurately merge the camera view and the model information. The main issue was that the model represented elements of the site that had yet to be built, and there was no assurance that the model was accurate enough to make correct geographical associations. The team recognized that to accurately and efficiently superimpose the complex 3D model information onto the panoramic photo, point clouds, or as the team called them, anchor points, would have to be created between the functioning interface layers. The anchor points ended up consisting of existing physical entities such as street signs, street lights, and trees within the project environment that could also be created and referenced within the 3D model. Upon completing the overlay of the 3D model information, the team separately incorporated and overlaid a live video feed into the panoramic view. As a final step, the project team fused both the model layer and the live camera feed layer into the panoramic view, as seen on the figure on the slide, the current slide. Upon completion, the 3D model information was both visible in the panoramic photo and the live camera feed, highlighted in the red dash marks you can see on the slide here. Here we have a video that just kind of give you an idea of what we accomplished within the first phase. Although this is not the the video we created within the first phase. This is just a sample product. Here you can see a panoramic photograph overlaid with 3D model information. The only augmented reality attribute missing from this example is the live camera feed that was incorporated into the phase 1 testbed. Simply put, this is a sphere dropped into a 3D model with a backdrop panorama painted onto it. So you could have a Google Street View throughout a city or throughout a building, which makes it very accurate when portraying this information. The model information added to the panoramic video includes service information associated with sanitary sewer layout within this city block. Just to give you a little bit of clarity about the technology we used for this testbed, the team used a static PTZ camera to develop the live video feed and the 360-degree panoramic photograph. They also used 3D modeling software with point cloud capabilities, and they used Synthesize, a camera tracking and stabilization software that ultimately allowed for the overlay of the model information and live camera feed onto the panoramic photograph. What might be most important to take away from this is that currently there are hardware and software devices in use that can support a significant level of augmented reality capabilities. So in other words, the majority of the technology is there, but we just need to manipulate it to meet our goals for augmented reality. Based on the technology created to date, the results of the first testbed have revealed the following benefits. This level of augmented reality allows for a more thorough review of upcoming work to be performed, and as a result, can provide insight to the most logical placement of on-site materials. In addition, it allows teams to track and observe field personnel's routes, productivity, and more easily verify they are working on the correct project activity. In addition, used in conjunction with a project schedule, this level of augmented reality enables very thorough schedule reviews and analyzes providing project and schedule look-ahead verification. These benefits mainly derive from the ability to actually view the progress of the work in relation to the overlay 3D model. So in other words, this to-date technology should facilitate the ability to visualize which specific activities are being performed by specific on-site labor teams. Some of the lessons learned from this first phase. The project team was uninformed in regard to the different protocols necessary to locate the camera application programming interface information, which led to significant delays during this project. The camera software development kit also ended up being problematic. The code examples were inadequate, and much research had to be performed to correct these issues. Calibrating the camera wasn't possible, which led to several limitations with regard to accurate panoramic-based tracking through the live video feed. We also received slow feedback from the camera, which caused offsets and latency of information in the live video feed overlay within the panoramic views. We also had issues with wind. The wind heavily affected the PTZ cameras, and based on the distance between the cameras and the project site, even minor movements would cause significant shifts in the overlay 3D model, rendering model information misaligned, or misaligned information with the panoramic views. In regard to the point cloud methodology, the final model overlay was not perfectly aligned with the panorama. Point clouds that only included points along the road were not enough to accurately overlay the 3D model onto a panorama to attain stable pose. So to improve the use of this technology, another iteration of this methodology may have to be developed. Despite the aforementioned issues, and based on the fact that a live video feed and 3D model were effectively overlaid onto a panoramic view, the project team deemed the end result a success and confirmed the feasibility of utilizing augmented panoramas for the use of on-site monitoring. The augmented reality project team, the second phase of this project was performed in an underground railway station on Bond Street in London. And the augmented reality project team chose the Bond Street Underground Railway Station project site in London due to its confined underground location. The project site location basically simulates conditions which you'd see as you would see inside of a building, in which fixed live stream cameras on site would prove ineffective, and the accurate service of real-time location services such as GPS would be impossible. The team used this distinct opportunity to prove that 3D model information can be overlaid onto a visual flight path, or in this instance, a recorded video stream. The first field trial was designed to simulate a first-person view of a project site walkthrough and serve as a proof of concept for overlaying simplistic data onto a recorded video stream. For this exercise, a 2 or 3 minute video stream was recorded. This was achieved by simply placing a camera on a worker's hard hat and having the worker walk through the project site while the camera was recording. MicroStation was then utilized by the project team, and MicroStation, if you're not aware, is a 2 and 3D modeling information software, to develop a 3D flight path that mirrored the recorded video stream. Again, with the use of SynthEyes, the project team was then able to attach the fabricated 3D flight path onto the recorded video stream by utilizing pixels within the recorded video stream as anchor points. And basically the anchor points consisted of X, Y, and Z coordinates within the flight path, or the 3D flight path, that were systematically matched to known marker points established in the field. Once the team was able to successfully overlay the 3D flight path onto the recorded video stream, they were then able to start incorporating virtual 3D images. The recorded video stream was first overlaid with simplistic model data, and then more complex images as seen in the picture on this slide. The second field trial was designed to simulate a signal sighting exercise for locomotive conductors and act as a proof of concept for overlaying complex data onto a recorded video stream. The recorded video stream for this field trial was developed by placing a camera on the front of a locomotive and having it pass through the mainline station while the camera was recording. With the use of a laser scanning device to help position existing on-site information, the video was then synchronized and overlaid with complex 3D model information developed with the use of MicroStation. Similar to the first field trial, the model information overlaying process was performed with SynthEyes, and with the use of MicroStation, 3D model signal information could be relatively easily added, altered, or removed from the recorded video stream overlay to develop varying simulations for the conductors. So here you can see this is another sample video. In the first bit of this video, we can see is the ability coming up in the next couple seconds is the ability to add and remove information. You'll be able to see a steel bridge or a gantry being removed from the video. Soon you'll see some model information appear onto the video in a second here. Okay, and as we move into the next segment, you'll see the mock station model. It's a combination of design tracking information and survey information. And you don't need any additional software running while performing this evaluation. Soon after this, you're going to see some point cloud information appear. The good thing about this is it will produce obscurities. In other words, say a signal or a signpost is being obscured by foliage or a building component, you can easily recognize that with the point cloud information overlaid into this video. Upcoming here, you can see adding a new signal and changing its color. And when you move backwards and forwards again through the station with the point cloud, you can see that particular signal location that's obscured by one of the signs hanging off the overhang, and then you're going to correct that issue. And here you can see him correcting the signal being obscured. Okay, so hopefully that gave you a good idea of some of the progress we've made thus far. So just to again give you an overview of the technology we used for that, a simple recording video device was used to capture the video feed. 3D modeling components were developed with the use of MicroStation, as I previously mentioned. On the right-hand side of the screen here is an example of a 3D flight path we developed through the use of MicroStation. And Synthesize was then used to overlay this information into the live video stream. And similar to what I mentioned earlier, provided the technology used, this suggests that existing software is up to par in relation to the ability to support the level of augmented reality technologies. So both field trials produced results that were found to hold business value. The Bond Street Underground Railway Station project was able to utilize the field trial concepts for on-site applications. Upon completion of the first phase 2 field trial, the Bond Street construction team recognized that on-site walkthrough video recordings could be used to support safety training and toolbox talks at the beginning of each day. And the team pointed out that the recordings would be especially useful in terms of avoiding safety infringements, basically by highlighting safety zones in the recordings with the use of 3D model data and showing that to the on-site workers. The second phase 2 field trial was found to be equally useful. The locomotive company found that the final product could be used as a training program for conductors. In addition, the recording saved a significant amount of time during the design review process, and instead of having to perform in-field testing to anticipate visibility of signal sites, the recordings overlaid with the 3D model data from MicroStation could be used to simulate this process. Sorry about that. Here we go. Sorry about that. In its entirety, the Phase 2 testbed yielded thorough and positive results. Crucial to the future development of augmented reality, the team concluded that when attempting to overlay 3D model information into a video stream, the need to identify the speed, direction, and distance of objects within the video stream is crucial. This allows coordinates identified within a simulated flight path to be appropriately aligned with the video stream's similar object coordinates. The project team was able to determine that the merging of simple and complex data onto a recorded video stream utilizing a mobile camera device is feasible, and the established Phase 2 proof of concept testbed technology provides a definitive link to developing a live video stream that can be merged with real-time location service technology and overlaid with 3D context. So within this next upcoming year, now that we've completed the first 2 phases of the project, we plan to initiate Phase 3. Following the Phase 1 and 2 test beds, the research team began literature review in regard to the application of accurate real-time location data and information streaming for augmented reality. And basically at that time, the team discovered that current technology standards are insufficient for the uses of augmented reality the research group was attempting to use them for at the time. So to make augmented reality a more powerful tool, current technology standards will need to be refined, including the ability to stream larger amounts of data than currently exists, and the need for more accurate real-time location services. The team determined that this may take a few years of research and testing, and to obtain the full value of augmented reality, and an investigation is going to be needed to fully integrating all the technologies previously illuminated within Phase 1 and 2. Based on the research team's findings, the team has recommended next steps that may facilitate the future development of augmented reality technology. Phase 3, currently being designed, will focus on advanced asset knowledge through augmented reality, and this phase will be supported by Fiatech and is anticipated to include the following activities, including a more comprehensive understanding of real-time location service technologies, how real-time location service systems can achieve levels of accuracy suitable for effective deployment, and to support the use of augmented reality applications and solutions. The team's planning to analyze the business benefits the enhanced capabilities of augmented reality can provide to the point of activity worker, and essentially develop a pragmatic approach to the deployment of augmented reality. Skip this slide there, sorry about that. So for the field trials in the next phase of this project, we're going to look to develop guidelines for field implementation with reference to accuracy of various technologies and task needs, and secondly, identify implementation targets with respect to necessary accuracy that can guide technology development to improve fitness to task. The final project is anticipated to be to be able to readily access asset knowledge by merging simple and complex data onto a real-time view produced by a mobile camera device. The device should be able to effectively align 3D modeling data at the right position, orientation, and pitch depending on the user's location, a feat which Cont'd, Place, and Network Rail have been working on and successfully accomplished over the past several months at the London Bridge Station project. The initiative has allowed Cont'd Place to visually communicate the work that will be undertaken for the London Bridge project without having to physically commence the work, and basically it's allowed Cont'd Place to scope the temporary works without disrupting station operations. The final puzzle piece will include the device facilitating on-site asset management through augmented reality by providing context-sensitive data and specific information regarding real-world objects. So in other words, augmented reality should be able to readily access asset data through a simple click or touch of the screen while pointing the camera device at a piece of equipment, material, or activity. And at this point, I'm going to hand it over to Manny.
Thank you very much, Justin. So I'm going to start introducing you the future project that Fiatech has planned, which is a Phase 3. And I've been very fortunate that our team has started being involved in this activity. So I'm going to introduce you a new type of augmented reality that by short we've called it MARS. It stands for Mobile Augmented Reality. The application that we've envisioned for our system is real-time field reporting. So on this slide, you can actually see a tablet. The idea is that you would be standing on the job site and you would be able to perform your daily field reporting activities. Whether this is completing your daily construction reports. So here you can see a number of elements that have already been annotated by the user. And you can actually see the DCR information that are being associated with them. What we do is we essentially capture this information in 3D, and we would like to make sure when the user actually walks into this space, not only they have the authoring capability, which is the capability of adding this information, but they can always retrieve this information no matter what viewpoint they have. In addition to that, we would like to make sure that they can also receive the specifications. So this is not only limited to the construction phase, obviously this also has applications to the operation and maintenance phase of the project. So again, in this case, you would be able to access instructions for operating and maintaining different equipment, or you would also be able to perform your reporting for facility management purposes. So we've been working on this idea of being able to bring augmented reality to tablets on job sites. This is a project that we started about 2 years ago when I was at Virginia Tech along with Jules White and Hyojun Bae, our students, and the three of us, we started working on it, and we prototyped the system, and it was actually licensed out to start a company. What we offer in that capability is essentially SDK that provides millimeter level accuracy of putting overlay information on real-world three-dimensional objects. So you can be standing on the job site without using any markers, without using any location tracking module, no GPS, no wireless. You can capture a photo. The photo goes into our server. On the server, we localize your location and orientation, and within about a second of time, we essentially provide the information. You can get access to specification, project milestones, other photographs that have been captured on that area, or any other report that might be available. So how does this process happen? As I mentioned, we don't use location tracking. There's no need for markers. So what we actually do is we benefit from existing photo collections on job sites. There are two ways that we essentially use these photos. We have a web-based interface where users will be able to upload their daily photos. There are also apps, iPad apps, and we also have an iPhone admin app that allows users to be able to upload the photos. So given the number of photos, you can actually upload these photos into the server. And during the daily reporting activity, the user would essentially start creating overlays. What we do is on the server side, we take these photos and we generate a three-dimensional point cloud models. All these overlays, whether they happen to be the DCRs, QA/QC reports, punch lists, everything would be augmented through the photos on this three-dimensional point cloud model. So this point cloud, like I said, it's directly generated from the photos. There's no need for any laser scanning device to generate it. Once we have this model on the server, then essentially you'll be able to go to the job site, and no matter what view or scale you have with respect to the element, take a picture, and essentially be able to access the information that we have on this on the system. So here I'm actually going to show you these two capabilities over video. Like I said, the first capability is to make sure we would allow the users to essentially add information. And these informations could be DCRs, field reports, or specs. Our work really doesn't focus on generating the user interface. Rather, we've been focusing on creating this mobile augmented reality technology which doesn't need the markers. So essentially in this case, you can actually see a user would stand in front of certain construction elements. And this is a very simple interface that we have which allows the user to essentially create the overlay. So let's say, for example, a user is interested in selecting a certain part of one of the facade elements. As you can see, a certain number of points will be selected. Then through this interface, you can attach your reports. These reports could be customized based on the type of application you envision. In this case, we have an observation report for field that we are actually piloting with one of Fiatech members. And in this case, you can actually see information would be imported into the system. So I'm going to slightly advance this video. Again, in this case, you can actually see all the information are typical information that we have on daily reporting activities, but now the user would be able to also retrieve the same information. So again, the process is the photo is captured on the client device, it goes into our server, and it comes back to you with information that is augmented. So the user will be able to click on it, and they will be able to get access to the same information. I'm going to advance this a little bit. Now, I'm also going to show you that this system also works indoors, so it doesn't necessarily need to be outdoors. As long as you have benefited from your existing photos, these 3D models would be generated, and essentially you can start interacting with them. So in this case, as you can see, the user is taking a photo, and 3 reports are already embedded into the system, and these reports are coming back to you. In our process, we have different types of models that could be generated from these photos. For example, for one given project, we can have multiple models. These models could be made because there are cases where we have identical rooms or identical spaces, or there are also cases where we would like to capture information in 4D, which is 3D plus time. So our admin interface allows you to generate generate different models. The users essentially have different levels of accessibility to this environment, and as I mentioned, you can generate your own customized reports, whether these are DCRs, QA/QC, RFIs, or even you can use it for O&M during the operation phase of the project. Here's some of the snapshots of the interface. On the left side, you can actually see a number of different sites that have been created for the same project. On the right side, you can actually see the photos that have been captured using the app, and they've already been placed into the system. So again, what we do with these photos is we generate a 3D point cloud model. On the server, the user can actually start adding the information to it. So on the left side, you can actually see the user has annotated a number of photos, and the number of reports have already been attached. Like I said, this technology can also work indoors, so we've already tested it, and I'm showing this indoor example as I'm going to show you how this has been integrated into Google Glass in a moment. So one of the capabilities that we have is also being able to filter information. So based on the level of access that users have to the system, they can access different levels of information. So here, again, very simple prototype where you see a number of annotations in the scene, and now you can actually remove some of them. Again, based on the level of access, we can filter out some of this information and only provide information based on the need. So we've actually been testing this system for the past 2 months on a number of job sites. So here's one of the applications where the superintendents are using this for daily reporting purposes. So every day, or as often as significant progress is being achieved on the job site, they go out, they take photos. Again, what we do with these photos is on the back end, on the server side, we generate 3D point cloud models. The users on the site, they choose certain elements, they annotate these components, and essentially information is being embedded to them. So here you can actually see these reports that are generated. Screenshot of the checklist, which in this case happens to be for a column. Again, whatever information you want could be embedded. We've tested this system for different viewpoints. On the right corner, you can actually see, based on different distances and based on different viewpoints, the user should still be able to retrieve the same level of information. For every day you're taking photos and you're conducting your daily reporting, you can have a synchronized set of these reports that are coming back to you that essentially shows which one of these photos have been augmented and when this was actually done. We still are conducting our pilots, so some of the aspects that we are doing research on and experiencing is essentially checking for resiliency and computation time on site. We've tested the system under various lighting conditions, and indoor and outdoor. And in this case, on the slide, you can actually see we've tested the level of performance under different levels of occlusion. So on the left side, you can actually see the shorings. On the right side, you can actually see there's an equipment that is moving in front of the camera. We still have the capability of recognizing the scene and providing the content back into the user. So I already showed you a video, and here's a link to that. You can actually see if you are interested in trying this technology, we do have an app that is currently available on Apple Store and Google Apps Marketplace. You can search for that under PowerWorks Mars, which again, it's mainly intended to show you the capabilities of testing this technology in a small scales or even in larger scales, indoors and outdoors. Like I said, we don't really focus on creating the interface. Our focus has been making sure our platform is accessible. So we've created a fully open cloud service that could be embedded into any app. So if there are companies that are interested in using their own apps, they can essentially benefit from the SDK that we've created. Now, we've also had cases that people were interested in using this without using an app, so we've actually come up with a solution for that. We do have HTML5 implementation of the same interface, where the users just need to have access to an internet browser. Then again, as long as they have the capability of taking a photo on their smart devices, they should be able to upload the photo through the browser. We process it on the server. On the browser, we provide the information back to the user. We've also tested a capability of texting images to our server. We've notified this as one of the needs, so we've actually come up with a solution for that. We have made attempts on benefiting from existing laser scanning point clouds, video-based point clouds, or RGBD point cloud models. So we can actually use those to generate the underlying model that is needed for creating augmented reality. Now, oftentimes, when we are presenting the system, discussion comes up whether we have capability of integrating to Google Glass. We've been very fortunate that we've been recipients of the Glass through the pilot project that we have with Google, and you can actually see how this technology is actually working in the Glass. So the SDK that Google currently offers doesn't give us complete access to the camera, so the workarounds for that, and this is just a simple interface you can see. So right now the user is using essentially the Glass, it's taking a picture. In a moment you're going to see the same picture of the room that I mentioned to you. The image is being captured. Now we share that photo on the Glass with our CarWorks Mars app. Once it goes into the app, it goes on the server. It's being processed. Right now it's being shared. In less than a second, it identifies the location and orientation of the user, and it comes back with the overlays. So again, you'll be standing in the same room. You can change your viewpoint, but see the photo that was captured is being processed. So you can see a note that is actually popped up in the center part of the screen. Here's another one that, for example, you can see another overlay in the same room. Again, even on the Glass, you have the capability of filtering and providing information based on the need. Here's a third one that's showing another level of information. Like I said, the benefit here is that there's no need for markers and there's no need for location tracking. So as long as you've had photos captured from this space beforehand, we should be able to offer this capability. Now, I would like to just use a slide that was presented by McCarty Construction in a recent annual conference by Fiatech, which I really like it because it actually captures the state-of-the-art practice. So if you happen to have field conflicts and you need to have users be provided with instructions, the current practice is people typically use existing apps, they take notes, they take pictures, and what they do is essentially they send this information back to the people that are sitting in the trailer or in the main office to analyze the data, typically using building information models, locate that information. What essentially happens is people take snapshots of these building information models, or they also provide access to a specification and send them back. So this analysis and the presentation was made shows that the state-of-the-art practice stays somewhere between half an hour to 5 hours from the time that the conflict is being observed on the site until the time that the team on the site can provide guidelines for the subcontractors. So what we're essentially doing with our system is we are trying to see if we can minimize that time to get access to information to minimal amount of time. So a user can take photo on our system. It only takes less than a minute from the time that the photo is uploaded to the server to get augmented. Then we essentially provide access to the specification or all these kind of reports that I showed you. In Mars version 2, we also have the capability of providing access to 4-dimensional building information models, or a system that I have previously been working on, which is called GIF-AR, stands for 4-dimensional augmented reality, and I'm going to present that shortly. So there are two key issues that essentially differentiate this solution from any other existing method. One is because everything in our system happens to be sitting on the server, the user can always access to the most updated information, whether this is the BIM or field information. The second issue is the problems that most existing apps have with rendering a complete and rather updated billing information model. So what we do is we take care of the rendering on the server side, so user doesn't have to worry about that on the tablet device, and essentially the image comes back to you with the billing information model overlaid on it. So I'm going to take a few moments and essentially show you that capability of bringing BIM into the picture. So on this slide you can actually see the application of this for project level monitoring. What we do is we take an existing billing information model that only shows elements to the time a photograph is being captured. We take that 3D model, we overlay that on the photo, which the location and orientation is already known to us. We can actually go through the schedule information. So in this case, we have a 4D billing information model based on expected level of progress on different activities in the schedule. We can perform an analysis and figure out state of progress. And essentially what we do is we provide the user back with a photo that shows the billing information model overlaid on the photo. And in this case, we are providing progress information. So for those elements that happen to be ahead of the schedule, we show them in green. And for those elements that happen to be behind, we show them in red. So this was a system that we've been working on prior to the Mars system. So initially we started focusing on fixed cameras, and then we started benefiting from existing photos. So here's just an example of these photos. Like I said, our system completely benefits from these photos. They can essentially represent different elements. They can be captured from different viewpoints. They can be captured for safety reporting purposes, productivity reporting, quality control. What we do with these photos is essentially a 4-step process. First step, as I mentioned previously, is we generate 3-dimensional point cloud models given a set of photos. For photos that are being captured over time, we can generate separate point cloud models. We can overlay these models. We superimpose the billing information modeling on this point cloud model. And lastly, we automatically analyze physical progress to understand deviations. And based on a metaphor of traffic light colors, we are providing this information. So I'm just going to quickly show a video that's going to take another 30 seconds. So this is just an example of the model that is supporting our mobile augmented reality capability. This site is generated using 162 megapixel photos. So a user has walked on the sidewalk around this basement area. They've captured the photos, and you can actually see the point cloud that is generated. On the left corner, you can actually see the location of the user that was holding the camera. Right over here, you can actually see the camera frustum. So in this case, as you can see, the user during the data collection was walking along the sidewalk capturing these photos. You can zoom in and you can zoom out and capture whatever information you're interested in. We can dive into any of these camera viewpoints, and you can see the site from that perspective. So in a moment, you're going to see the viewpoint of that camera that shows the basement that was under construction. There's an excavator in the back. There's a steel structure on the left side of the image. Everything is in 3 dimensions, so the user can actually make measurements. We can also overlay the photo that was used to capture the scene. So not only you see the scene using the point cloud model, but at the same time you can also have the photo and point cloud being visualized at the same time. So this is again the capability of capturing these as-built point cloud models purely based on the photos that have been captured either through still cameras or smart devices. I'm going to quickly advance this just to show you when we bring billing information modeling into the scene. So this is the existing point cloud model. The billing information model can come back to it in a moment. That would be overlaid on the point cloud, and the user would be able to see what is the expected performance of the site versus the actual performance. This billing information model is IFC, so this could be exported from any Bentley package or any other Autodesk packages that have the capability of interoperability with IFC models. So in this case, you can see the photo, you can see the 3D elements, and by changing the transparency, the user can actually interact with the entirety of the scene. So on top of this system, we've created this capability of automatically color coding. So those elements that are on schedule, they appear in green, elements behind red, and those elements that are not assessed, their colors essentially don't change. We've essentially looked into different applications. As you can imagine, this has applications for communications, safety management. We've also done some experiments as to how this may help with coordination meetings for lead documentations. Just to summarize what I showed you, in the upcoming project for Fiatech is that we have a capability of providing markerless and infrastructure-independent augmented reality. The benefit here is to use existing devices. The companies that we are piloting with, one of them has more than 100 iPads on the same site, so they're really tapping into their existing resources, not adding any new hardware. We host every information on the server, so you have always access to latest information. We can work with videos, and as I mentioned, this could be embedded in any existing apps, so it doesn't necessarily need an app to be working with. There are 2 ongoing projects. We've been very fortunate that Zachary and Turner Construction have been supporting our work, and we are testing not only the technology, but we are also focusing on coming up with the right guidelines for process and organization that can support successful implementation of this technology. Having said that, I just want to quickly acknowledge the people who financially sponsored this work: National Science Foundation, Allied Minds, which is the group from Boston who sponsored this startup company, PowerWorks, and a number of contractors and owners who've been very helpful to us, providing us with access. Having said that, I would like to open up for questions, and I'm going to leave you with the contact information of the presenters today. And thank you very much for your attention. Melissa, are there any questions for us?
There are a few questions, Manny. If I could just go through them. Just give me a second. One of the questions we've got here is augmented reality, can it be used for facilities maintenance? That was the first question. Manny, if you'd like to answer that one.
Absolutely. If you can also please give me the control so I can show the last slide that we had. Thank you. Yes, it's actually easier for us to use it for operational maintenance because the user doesn't need to frequently update the base model. The process that we've envisioned for facility management is a user would essentially walk into the space, they would capture photos of the entirety of the space. They would add all the reports, all the information that they need to, or they are interested in having for facility management purposes, and then they can start interacting with the scene. Now, the benefit here is that if there are owners out there that they don't necessarily have building information models available to them, our technology can still support facility management purposes without using BIM. So a user can associate information directly with the photos. And I think this is the key differentiating component of this technology. Obviously, as I showed you, we do have the capability of leveraging BIM. If that happened to exist, even better, we can store that information, and that's something that we would be happy to do additional pilots if there's anybody out there who's interested.
Okay, thanks, Manny. The next question I've got here. Do you understand that technologies like Google Glass are going to be more feasible through augmented reality for everybody in the industry, or are we still very far away? I think you probably answered that in your presentation, but if you'd like to add to that.
Absolutely, and this is a great question. I am passionate about variable displays. At the same time, I'm concerned. I am passionate because I think there's a lot of potential in using these devices, but I'm concerned for safety reasons, and I'll get into that in a moment. One of the things that we've tried to do so far with our markerless technology is essentially to bring this to existing devices. There are many contractors and many owners that have already invested in purchasing smart devices and tablets on job sites. So what we really wanted to do is to use existing hardware as opposed to introducing a new component. The glass, as of now, comes at a significant premium. It's a great device, but at the same time it has that challenge. Second issue is this notion of providing real-time overlays, I think the capabilities of rendering sometimes limit us from being able to show 3D elements exactly at the same time a user is looking to certain elements through the video that is capturing on these devices. So what happens is that there's always a delay from the time a user sees an object from the time that the 3D element is overlaid on it. This delay can create dizziness. It can create a little bit of motion sickness. So I think there are still issues with respect to safety of using these devices on job sites. But for now, like I said, the solution could be we can still use existing tablets. The user can take a photo. The photo goes into the server. We find the location and orientation. We provide the information. So not real-time augmented reality in the sense of seeing the information, but with minimal amount of time, you always access information. Hopefully this answers your question.
I don't think we have any more questions have popped up apparent, Manny. If anybody has anything else.
Great. So we have our contact information on the screen, and if there are any questions or if anybody's interested in looking into any of these demos, you can contact Fiatech or any one of us. We'd be happy to interact with you and follow up through Fiatech.
Okay. Thanks, Manny. Thanks, Justin. We've come to the conclusion of our hour. We're just over, actually, a couple of minutes. But thanks to everybody that spent their time with us today. Be reminded that the recording will be made available in the webinar archives on the Fiatech website within the next few days. Thanks again, Manny, Justin, for sharing advancing asset knowledge through the use of augmented reality technology with us today. Please contact Fiatech or myself if you'd like to get involved with this project or have an idea for a future webinar to advance capital projects in industry. Have a great day, everybody. Thank you.